Good evening, Mikkel. He's currently a PhD student at the University of Hull, where he's studying dwarf galaxies with active galactic nuclei, AGN. This particular subset of galaxies is not well studied, and the tools we usually use have some problems in this galaxy regime. Before coming to Hull, he was a science communicator at the Planetarium in Copenhagen, where he worked on outreach in astronomy and astrophysics, as well as developing exhibitions about space. This line of work put him in touch with people from both research and industry, so he has quite a wide range of subjects. So please welcome, in a Mexborough Swinton way, our guest speaker tonight, Mikkel Kristensen.
Mm-hmm. Thank you very much, Stephen. I will share my screen then. Let me see if... So I've never actually... Oh, is that the right screen?
That's the right screen. Active galactic nuclei. I can see your notes, though.
Right. Okay. So if I do a small switch, so share this one. That should be the right screen.
That's the one.
Excellent. Right. So thank you for having me. I do quite enjoy doing outreach, and I've been in touch with a few astronomical societies here while I've been in Hull, and it's always been I've always had a very nice time when I've talked with them. So thank you very much for inviting me. My talk is about active galactic nuclei and quasars. I have if any of you want to write me, you are more than welcome to. I have my email in the presentation here, so you can feel free to write it down. So the overview for my talk today is first a tiny bit of history and background of AGNs and quasars. Then I will go on to talk about the anatomy of AGN. So we will break down all the different components in an AGN, see where they come from and why we believe AGNs are the way they are today. We will then look at where and how do we find them. So this is a bit more, I guess you can say it's very much what recent research on them, where we are with that. And then also after that, a bit about their role in galaxy evolution. They are a somewhat debated role. Some people think they are very important, other people think they are not very important. I think they're very important, but there's a bit of debate about that. And then finally, just a tiny bit about my research. So first up, a bit of history. When I say history, I really go way back. So this is more than a century ago, because back in the beginning of the 20th century, there was not really, there were galaxies in the sky, but they were called nebulae because they looked like planetary nebulae, or like just all of the clouds of gas that astronomers could observe. But sure, there were some of them that had some spiral structure, but it was a bit uncertain whether they were nearby or if they were far away, what the size of them were. So in 1909, then and Edward Arthur Fatt, he took some spectra of some spiral nebulae and globular clusters, and he noted that they have a very distinctive, they have very similar spectra. From his paper that I had to go into the archives to find, this is you have the fourth spectra, you have the solar spectra, the Andromeda Nebula, a spiral galaxy, a spiral nebula, and then a globular cluster. And as you can see, all of these, they are very similar, at least, especially the spiral nebula and the globular cluster. So there seems to be, okay, so maybe these spiral nebulae, they are consistent with being a collection of stars. How many stars that was a bit unsure because they did seem to have also similar intensities to the globular star clusters that we could find nearby. So it was by then still a bit difficult to tell apart. And then in 1917, a Schleifer, I think that might be the pronunciation of that. He commented. I found an excerpt from his article that so they were looking at emission lines, and these emission lines were consistent with globular clusters, but they seem to be very much broader than what you would expect. So when something is very broad, it means that whatever gas you're looking at tends to rotate with very high velocity. So this seems to be a bit inconsistent with just being a globular star cluster. These spiral nebulae, they seem to be rotating a bit faster than what was expected. And then in 1920, perhaps many of you have heard about this, the great debate before. It was by two astronomers, Shapley and Curtis, and they discussed about a number of things, but one of the things they discussed was, are spiral nebulae, are they in the backyard of the Milky Way, or are they extragalactic sources? So are they sources beyond the reach of our Milky Way? And Shapley argued that spiral nebulae are clouds of gas that is in the Milky Way, basically that the whole universe is only confined to the Milky Way. But Curtis, he believed otherwise. So by then it was already established that the Milky Way was hundreds of thousands of light years across, and those scales are just huge. So for Shapley, that was one of the arguments, that these are just enormous scales. It would be very weird if something was larger than those scales. But Curtis, he argued otherwise, and I can see there is a slide in between that I have very quickly jumped over. But this debate was finally settled 9 years later, almost a decade later, by Hubble. So he looked at the large Magellanic Clouds or nearby galaxies, and he looked at a certain type of star, a certain type of variable star called Cepheids or Cephides. And Cephides are, so a variable star is a star that their luminosity changes in a very predictable pattern. And that pattern, you also know both how often it varies and how bright its maximum luminosity will be, how bright it will be. And from looking at these variable stars in other galaxies, he could conclude that the distance to these galaxies would be enormous because the brightness is so low. The distance for the light to get to us is so low that it would have to travel not just the distance of the Milky Way, but even millions of light years instead. So this debate was settled, and that was sort of the start of this extragalactic astronomy, that galaxies, these spiral nebulae, are in fact extragalactic sources. Despite that, then, and now we're approaching the territory of active galactic nuclei, this distinction or this naming scheme, spiral nebulae, it kind of it stuck a bit. So this is from Carl Seifert's article in 1943, and he still called spiral galaxies for spiral nebulae. So some people are, I guess, a bit not conservative, but they are old school. They tend to stick with the way things were called once, and then yeah. But this particular paper is quite interesting because that was the one thing that Carl Seifert he noticed, was that there were some of these spiral galaxies that seem to have some very strange emission lines. So there is an actual spectrum from this article on the right, and what he noted in particular is that the width of these emission lines are very broad. And the reason the width of, I will explain and sort of motivate why the widths are important. But what he concluded is that they are unusually bright in the nuclear region, and the emission lines are unusually broad compared to other spiral galaxies. And this didn't receive much attention for various of reasons. These galaxies only just started getting some more attention in the 60s. This is just another, just to show you how far we have advanced. I think it's a very funny picture. So if you look at on the spectrum here, you can see there are these two pictures of NGC 4151. Today, the pictures we have is vastly superior. So certainly things have improved since then. And these are other two galaxies you looked at with these very unusually bright core region or nuclei regions. Now, in the 1960s, radio astronomy became a big thing. There were a lot of small and big radio telescopes, hobby telescopes even, that were being put up around the whole world actually. And they found a number of very strange objects. I only chose to include a review here. So in 1967, Margaret Burbidge did a review on quasi-stellar objects, because what a lot of radio astronomers had seen was a sort of a star-like object. One object in particular is the 3C 273, and it's the one you see on the right. And it does appear, if you look at it in both radio and in other wavelengths with other types of telescopes, it does appear to just be a star. And then you also see a sort of filament coming out. And that was one of the things that initially caught a lot of these astronomers out, is that this filament, this jet, is very unusual. It's very bright and extends very far, and it's observable even in the optical wavelengths. I've superimposed a more recent image of this object in particular, of this 3C 273, where you can see the radio emission. These are all the colored emission is from radio emission, at least especially the outline here, with some Hubble Space Telescope on top. So you clearly see that there is some sort of source, and from this source there is a lot of radio emission coming. These quasi-stellar objects, or star-like objects, people didn't really have a good idea what it was about. They didn't know what it was big, but one thing that was clear, and that was something that Schmidt in 1963 discovered, is that the redshift of this object is 0.14. If something has a redshift of 0.14, it's way beyond the scopes of our galaxy. It's even further out than the Andromeda galaxy. So what he concluded, rightly so, is that this is clearly not a star. It's something extragalactic. And with a redshift of 0.14, for something to be as bright as this object here, there was quite a lot of discussion about what can it really be, because the energy output for something to be so bright would be enormous, and people were arguing back and forth. There is I forgot his name, but there was one person in particular who argued very strongly that it must be perhaps so there were quite a lot of different explanations. One explanation was that it was a chain reaction of supernovae. Imagine you have a lot of very heavy stars in the center, and then one supernova goes off, it creates a shock wave, and this shock wave then reaches other stars, compresses them and sort of provokes them to go supernova as well. That could be one explanation. Another one is that just if we have a huge cluster, star cluster, then many of the stars, what if they explode simultaneously in a very short period of time? That was also suggested. Hoyland Fowler suggested a supermassive star, something that is 10 to the 8 times solar mass. We know now that that's not a, it's way above the size limit for a star. Anything that massive would not, it would be too bright and it would simply tear itself apart. So a star of that size is not feasible either. But then Salpeter and Seldovich in 1964, they suggested, what if it is, if you have a black hole and you have accretion onto this black hole, this supermassive black hole, and we're talking millions of times solar masses, that could explain it. It didn't receive too much attention, but then Lyndon Bell, not the, I forgot his name, George, no, Donald Lyndon Bell suggested, he explained this, he took this argument even further and said, it is sort of expected that we have a supermassive black hole at the center of a galaxy, and then if there were accretion onto this supermassive black hole, that could account for these very bright objects that we see. And that theory stuck. It was worked on a lot further, and in the 70s and 80s, there were a lot of work into trying to figure out and coming up with new models about what these quasars and active nuclei, what they actually are. And I will explain you now what they actually are. Oh, right, okay, so I moved my picture. You can see there is a galaxy. You can also see that there is a very small red dot. That red dot is supposed to have been in the center of this galaxy. Bear with me, I think something with the compression of the images. I like to find the very high res images, and then I just compress them later in OpenOffice, and they tend to make funny things with the pictures from some time. But an ADN is basically something that happens around the supermassive black hole at the center of a galaxy. And just to give you a scale of how big it is, there is that red dot, and that red dot is at least 100 times bigger than everything else. Everything I will talk about in this talk is happening on that scale, actually even on an even smaller scale. It's something that's happening on the scale of our solar system. Okay, so when I say look at the core, the nuclei of the galaxy, it's actually, you know, you can sort of see, okay, if I sort of make a ring around it, it's sort of that sort of scale that the nuclei is, then that's not the size I'm talking about. I am talking about something that's only the size of the solar system. It's extremely compact. So what is an ADN? So this is a schematic. I apologize, I don't have any labels on it, but we will put labels on what the different things are later. But in the center, which is white on my image, you can see there is a small sphere, a small ball. So that's the supermassive black hole in the center. And around this center, there is a small disk. And this disk is what's feeding the supermassive black hole. This is from this disk that material accretes onto the supermassive black hole. Around this disk is then an even bigger disk, or actually more like a donut or a torus. It's sometimes referred to as the obscuring torus, but it's something that is from this end to the other end is the size of our solar system. You can also see all these small clouds. It's illustrated by these dots and these very irregularly shaped blobs. There are some that are close, and there are some that are further away. And then we also have these jets emanating from the poles of the supermassive black hole. So this is a very schematic view. something, when you're working with something this powerful, you tend to get a lot of artist's impression. This is not an actual picture. I should caveat that. I'm sure you know. But it shows a bit more, well, I guess I like this picture. It is, it does feel a bit more powerful than the other one, than the schematic. So again, you have the supermassive black hole at the center. This artist, for some reason, decided to make the supermassive black hole the brightest. The black hole itself doesn't emit any light. It's actually the accretion disk that does most of that. But you know, it's an artist impression, so it does look very nice, and it makes for a very nice desktop background on your computer. Now, to be a bit more technical about AGNs, here's the optical spectrum of a quasar. It's actually not one quasar, it's actually the average spectrum of quasars. I think it's 160 different quasars. So we can, this is just in the optical wavelengths, from, well, let's say from around 1,000 angstrom to 6,000 angstrom, or in nanometers, it's from around 100 nanometers to 600 nanometers. Yeah, we like angstrom. And from this spectrum, we can actually start to understand the AGN a bit more. So first thing is that we can see that there is a continuum. There is like a steady decline in the flux with wavelength. It's very, very bright. There's a lot of flux at the very small wavelengths in ultraviolet. And then once you go towards the higher wavelengths, you know, you can see that it has sort of leveled out a bit. So this is called the continuum flux, or the continuum of the AGN. You have a number of other features as well. One, for example, is all the emission lines, all the spectral lines. And these spectral lines tend to be very broad. In fact, they are so broad. If you look at the first one I have over here, this is Lyman alpha, and right next to it is nitrogen 5. Actually, let me just change to this view instead. So all of these emission lines, they can be identified. We know from which element that these emission lines come from. And these emission lines are so broad that they actually tend to overlap quite a bit. For example, Lyman alpha here and nitrogen 5 here, they are very hard to separate when you look at the spectrum. And just in case the whole emission lines and spectral lines, the thing that gives rise to these emission lines is it's a picture of spontaneous emissions. So if the very basics behind it is that if you have an atom, you have different electron shells, and whenever an electron goes from an outer shell to a lower shell, then this electron needs to get rid of some energy, and this energy is then emitted as this light. So that's the cause behind all of this. All of these emission lines, you have some gas with a lot of different elements in it. Something excites these atoms, these molecules, or these elements, and then the electrons in this in all of these atoms then they de-excite and emit some light, and this is the basic cause of all of this emission. I just want to show a bit how we can deal with some of these emission lines. So one way to manipulate them. So this is just an example. This is the full spectrum. If we see that, we can again identify two things. We can identify the continuum, and we can identify an emission line. In this case, it's H beta. One way to manipulate a emission line is the broadening. So the broadening of emission line comes from Doppler shift. Very this is just a phenomenological explanation. But imagine if you have a galaxy. We are, as an observer, are at the bottom of the screen. If we look at a galaxy, if one arm is moving towards us and another arm of the galaxy, and this galaxy is then emitting light, is moving away from us, the thing that is moving towards us is blue shifted, and the arm that is moving away is red shifted. And we also have the central emission. So in that case, we get the total emission line we get is the sum of all of these emission lines. But if we have our galaxy rotate even faster, the arm that's coming towards us is blue shifted even further, and the arm that is moving away is red shifted even further. So we get a broader emission line. And this relation between the width of an emission line is actually very clear. If we use Doppler shifting, but instead of the speed of sound, we have the speed of light, then we can, judging from the width of the emission line alone, we know how whatever is emitting all of this gas, we know what the velocity is. We know what the rotational velocity is. So in this case, with our h beta, if we have a rotational velocity of 500 kilometers a second, 5,000 kilometers a second, we have something that is this broad, and just judging from eye, it's around 25 nanometers broad, which is a quite broad emission line. On the other hand, if you have something that's only rotating with 2,000 kilometers a second, which is still a lot, but then we get a much narrower emission line. In this case, perhaps only around 10 nanometers. The continuum emission is, well, let me just go to this one first, because I think that it's nice. So what this tells us is that, okay, if we have an emission line that is very broad, well, if we have these clumps of gas that's very close to the central black hole, their orbital velocities it would make sense if they rotate around 5,000 kilometers a second. So it's from this region here that we get the very, very broad emission line. Conveniently, this region is then called the broadline region. On the other hand, we still have some pockets of gas that's orbiting further out. And in this case, they are still emitting, perhaps orbiting with only 2,000 kilometers a second. In this case, we have narrow emission lines. We have the narrow line region. For the continuum, this is just a mock spectrum, but imagine if you have a disk. So I don't know how familiar you are with black body radiation, but basically everything that has a temperature, it emits light of some sort. Our skin, my cheeks are very red now, so they would probably emit quite a bit of infrared radiation. The sun is yellow, and from that it emits a lot of visible light. So basically anything that has a temperature emits light with some sort of given function, and this function is called the Planck function. And depending on the temperature of the object that it is emitting, the higher the temperature, the more shifted towards higher energies your emission is. And in the case of an ADN continuum, what you actually have is we have the accretion disk at the center, and this accretion disk is millions of degrees. And if you sum up a number of these accretion disks with slightly different temperatures, if you just cut out this part of the continuum, so let's say from 2000 and onwards, you sort of get a similar fit. You get a power law that basically describes the continuum of the ADN. You also have a continuum in X-ray. That's from a slightly different. It's from inverse constant scattering. I won't go into detail. That's about that. But basically a lot of these in many wavelengths, we sort of understand the ADNs now. So we have the continuum. It's coming primarily from the accretion disk. That's especially the optical and the X-ray continuum. And then we have this torus, which is also heated up. This torus consists of a lot of gas, a lot of dust. So it's heated up and it's warmed and it emits quite a lot of infrared radiation. So the infrared continuum is, we believe, is coming from the obscuring torus. There's one thing I haven't mentioned yet. This is a very famous active galaxy very close by. It's Centaurus A. So the radio lobes, and which is also the thing that led to the initial discovery of quasars. I haven't talked much about them. This is not on purpose, but it's just because they are perhaps one of the things that are the most difficult to understand. The physics behind what drives a radio, what drives a jet, is actually quite difficult even today, even for theorists, even for people who do simulations. It's quite difficult to exactly derive the math and the models to have these radio lobes. Nevertheless, they are very, very bright. In fact, the energy deposited into these jets and these radio lobes is comparable to the rest of the energy output of the ADN. So it's not insignificant, the radiation we get from radio. Same galaxy, but now only viewed in radio, and you can very easily see that there is quite a the rest of the galaxy is not very emissive. There's not a lot of radio emission, but it's especially in the jets. And this emission from the jets is caused by something called synchrotron radiation. It's basically when you have a charged particle, a proton or electron, moving around in a magnetic field. So a rotational motion is actually, you accelerate the particle, and when you accelerate a particle, you emit radiation. So in this, but the thing is that this charged particle has to move with relativistic speeds, so it has to move close to the speed of light in order to even emit any emission that's viewable. And this synchrotron radiation, it sort of gives the way to the to the radio emission. This is more like a more complete spectrum of an ADN. We have this is not a very this galaxy in particular doesn't have a lot of radio emission. Like so on the x-axis is the frequency or the wavelength on top. To some degree, once you go to X-ray, you start talking about energy, and then you have the flux on the y-axis. So you can see there's a very this is towards the optical, and then you have, once you go to an infrared, and once you go towards higher energies, ultraviolet, you have even more, and you also have quite a significant amount of X-ray emission. Some ADNs tend to not have too much radio emission. Some ADNs tend to have quite a bit, and that perhaps can this picture can perhaps explain a bit more, because okay, so we have all the different components of an ADN, but what exactly are they, or like how do we actually see them? So this is the unified model of ADNs. We because what they didn't know back in the 1940s and 1960s is that the broad emission line spiral galaxies that Seifert looked at and quasars are actually the same thing. They didn't know it back then. It's something that, let's say, only recently in the 80s and 90s really got unified in a nice way. And the unification of ADN is basically the difference between an ADN and a quasar is just the power output. So quasars are the absolute beasts of ADNs. They are the most, the galaxy, the types of ADN that outputs the most energy of all the different kinds of AGNs. And the different types of AGNs, what we believe now is the reason for the differences is mostly just due to the viewing angle. The bright spiral galaxies that Carl Seifert, so you can see that the names of some types of AGNs are called Seifert galaxies. Some galaxies is just because we have an unobscured view of the accretion disk, of the broadline region, and the black hole. You have also type 2 Seifert galaxies, which is basically Seifert 1 galaxies, but without the broadline region and without too much of the optical continuum, because that's obscured by the torus. They are the same thing, we believe now, but just the viewing angle is different. And then you have even different types of galaxies as well. Sometimes if there is a jet present, it's not always an active galaxy has a jet present, but if there is a jet present, there is usually quite a lot of radio emission. So in that case, we have a radio loud quasar or radio loud galaxy. Sometimes we have radio quiet quasars or radio quiet galaxies. So that's where there is a lack of jets. On Wikipedia, there is this very nice table of the different types of AGNs. They are basically the same thing, all of them. Some are more powerful than others, but mostly it's just due to the viewing angle. So that's our belief of AGNs today. And then a sort of interesting question arises, and that is, where do we find AGNs? And the short answer is that it's kind of complicated. And the slightly longer answer is that it depends on many things. It depends on the host mass, how big is the galaxy. It depends on the morphology. Spiral galaxies tend to host more AGNs. It also depends on the environment, the redshift, how we define an AGN, and what wavelength regime we look. Just to go over this quickly, this is my graph. It's not a very very nice plot, but it does show a bit the dependence of AGN frequency on host mass. On the x-axis, we have the stellar mass of galaxies in a large survey, and then on the y-axis is the fraction of galaxies in a certain mass bin that of galaxies in that mass bin, how many of them are classified as AGN. There are BBT and WAN. It's two different ways of finding AGNs, but it does sort of show the same picture. Around 10 to the 9 to 5 times 10 to the 9th, we have galaxies the size of the Large Magellanic Cloud, and in them we see a very low fraction of AGNs. At max, we see about 10% of these galaxies. At the lowest, we have only a couple of percent. So it's very rare. Whereas if we go to, say, 10 to the 10, which is like a Milky Way sized galaxy, sometimes, depending on the method, you get a frequency of 40%. Sometimes we have to even go up to 10 to the 11th solar masses. So that's something that's 10 times the size of the Milky Way to have the highest fraction. So host mass is important. The morphology is important as well. This particular study looked at AGN and barred galaxies. They couldn't conclude that barred galaxies have a higher frequency. So one idea is that the bars would help AGN activity. They couldn't really find that connection, but there have been certain studies into this that did find a connection, that spiral galaxies are more frequent to host AGNs. It can also be about environment. Dense environment can be disruptive, perhaps, to AGNs, but also at the same time, maybe a dense environment is necessary in order to create AGN. Perhaps a disturbing galaxy needs to drop by in order for AGN activity to start. This is a bit more debatable. I will talk a tiny bit more about this in a tiny bit. Another thing is the redshift. So basically, are there certain periods, time periods in the universe where the conditions were more favorable for AGNs to exist? And it seems so. Today, it's not, AGNs are not very frequent, but at around redshift 1 to 2 is when the peak of AGN activity happened. It also depends on your definition of AGN. It ties a bit in with the next part as well, the wavelength regime, but how do you actually define when something is an AGN? Some methods use the different emission line ratios. Other methods just say it's after a certain luminosity, like if it's of a certain brightness, then we have an AGN. Some other methods are if the core emission or the nucleus emission, if that is equal to the galaxy, the host emission, or higher, then we have an AGN. So it's all a bit flip-floppy. It's not really something that is set in stone. And then finally, it also depends on the wavelength regime. This table again, it shows that some galaxies have broadline regions, for example. Some do not. Some have X-rays. Some only have weak X-rays. So it's not really something that is, it's not a clear-cut definition when we have an AGN or not. And just 4 very quick ways to identify AGNs is, first is the luminosity. Like I just said, usually an AGN outshines its host galaxies. This is a photo from Hubble Space Telescope. It's a bit old now, but they tried to subtract the emission they expected from the quasar, and then they could see the host galaxy. But what it shows is that if you don't subtract the core emission, then it's basically, if you have something very, very bright in any wavelength regime, there's a good bet that it is, and if it's consistent, then it's a good bet that it's an AGN. Another way is to also look at AGN variability. Some AGNs actually vary quite a bit, to even 10% in its luminosity over a few months. That's very short time scales for something to vary. But this is still a sort of very new type. And certain wavelengths, X-ray, tend to vary quite a bit. Optical is a bit more stable, whereas I think infrared almost doesn't vary at all. But it is one way to identify AGNs. Another way is to just visual inspection. Usually if you see jets of some sorts, it's a good bet that there is an AGN, that there has been a supermassive black hole that ejected all this material. And then finally, of course, you also have the ionization fingerprints. So basically different spectral lines. This is from my work. This is 2 optical diagnostics, the BBT and the Venn diagram. And what they both use on the x-axis is the nitrogen 2 over H alpha emission ratio. So you take the emission, you measure the emission from these 2 emission lines, take the ratio between them, and then see where they fall on the diagram. The ionization, or the temperature and all the emission from an AGN tends to produce somehow a tiny bit different ionization fingerprints. And you can exploit this in these diagnostic diagrams. And then just finally, a few mentions of why AGNs are important. So one thing about AGNs is that we believe that they are a phase that most galaxies go through. So we know today that all galaxies they have a supermassive black hole at the center of the galaxy, in the center, and around, but some are not active. So for example, our Milky Way, we have a supermassive black hole in our backyard, but it's not an active galaxy. It's not an AGN. It might have been in the past, but it's not here anymore. But what exactly decides when it has an AGN? What are the triggers? That can be quite important, because one thing that the AGN does is the feedback mechanism. It accretes a lot of material, and then this material is then ejected into the energy from this material, accreted onto the black hole, is then put out into the galaxy again. And this energy can be, energy input can be quite disruptive to a galaxy. Towards the higher mass a galaxy is, the heavier a galaxy is, the more important this is. In fact, I think if you galaxies the size of the Milky Way and larger, one of the main things that control star formation is sometimes believed in some galaxies are definitely due to AGN activity. So if you have a very active core, it can actually disrupt all the star formation activity in your galaxy. Another thing is that they are believed to have been somewhat important in ionizing the universe. There was a time where the universe consisted of a lot of neutral hydrogen. Today, all the hydrogen between galaxies is ionized to some degree at least, and this energy output from the AGNs and quasars are believed to be one of the contributors to this ionization of the universe. So with all this said, then how do we actually get an AGN? And there are, as far as I can just could string together, there are a couple of ways to do it. One is but what all of these methods have in common is that you need to transport fuel into the central region of the galaxy. You need to have the supermassive black hole being fed. One way to transport fuel into the core, into the central region, is through mergers. So if you have two galaxies that interact with each other, they can, all the gas that is rotating around, it can be disturbed quite heavily, and it can then have an easier time falling onto the core region. So we see quite a lot of the very strong AGNs. They have had recent merger activity. When I say recent, it's something, perhaps a relatively big merger in the last billion years. Another thing is the environment. So here it's what we call a tadpole galaxy that is falling into its environment and into its cluster. So you can almost see the direction of this galaxy. It's moving up and to the left, and what it's doing is like it's moving through some gas that is between the galaxies, and this gas is then stripping and disturbing the gas in the galaxy, and this disturbance is also suspected to be a trigger for some AGN activity in some galaxies. And then finally, it's also just accretion of this intergalactic medium. Between all galaxies, there is at least some part of some sort of material, some sort of gas. Although it's not dense at all. It is, if you have some regions perhaps are denser, and if you have enough time, you have the ability to accrete this material onto the black hole and the central region. There are a number of other ways to do it, but so the mechanism they all have in common is that they are efficient at transporting material into the core region. So this pretty much concludes what you need to know about AGN, I think. I have a few mentions about my own research because I think that's also very important and very interesting. So the first project I've been working on is dwarf galaxies with AGN characteristics and their environments. So I mentioned already that AGN frequency, they are not very frequent in dwarf galaxies and galaxies like the large and small Magellanic Clouds. But there are some, and quite a few actually. But do we actually have reason to believe that they behave similarly to regular galaxies? because all the diagnostics, all the models for AGNs they are developed to regular galaxies like the Milky Way. So do dwarf galaxies follow a similar trend? And the answer is yes and no. At least regarding environment, they seem to be not care. I just mentioned that one of the AGN triggers could be environment, this middle picture. But for dwarf galaxies, that does not seem to be the case. It doesn't seem to be more favorable in dense environments or more favorable in isolated environments. Perhaps there are pros and cons in each, but then they sort of still level out, so you can't actually find any difference in the frequency of AGN, dwarf AGNs depending on environment. So that's the first time that has really been studied in detail for dwarf galaxies. It's a bit funny saying it's a null result in the sense that there is no dependence, but it's still a very important thing to consider. And I'm still continuing working on this, but now I've moved on to a bit more of simulation data. Because one thing that I thought is that perhaps it's because also the AGN trigger is delayed. Maybe if it goes through an environment, in a certain environment, it doesn't trigger AGN activity immediately. So that's one thing I've been working on now, because with simulations, I can piece together the complete cosmological history of galaxies. So perhaps dwarf galaxies that show AGN activity today, I can backtrace their history in simulations and see, have there been any significant events in their recent past that can explain this behavior? And it seems there is some things that dwarf AGNs seem to have had a slightly different cosmological history than just regular dwarf galaxies. But this is still in preparation. It's not a finished project yet. So just to do a quick summary, AGNs and quasars were not really known or studied until the late 60s, and the mechanism not explained until the 70s. And the unified theories began in the 70s. An AGN consists of the supermassive black hole in the center. That's the engine of the whole thing, with an accretion disk that gives rise to the continuum. There is the obscuring torus around it and orbiting emission nebulae that gives rise to the emission lines and the infrared continuum, and jets give rise to the radio emission. AGNs are found more frequently in high mass galaxies, and different AGNs prefer different types of environments. Stronger AGNs tend to be found in more dense environments and mergers. They can be found by a number of methods: by luminosity, by variability, visual inspection, and spectral fingerprints, depending on the wavelength regime you're looking at. Their importance in galaxy evolution is not to be underestimated. Even in dwarf galaxies, on large scales, with large galaxies, there is definitely they are important for regulating them. But even though it's sort of established, there are quite a few things that are still very hotly debated today, especially when it comes to triggers, environment, and the impact of them. And with that, I will say thank you for listening.
Mikkel, thank you very much for a very interesting talk. A question from me whilst the rest of the audience is thinking. We have a black hole at the center of our galaxy, Sagittarius A. Mm-hmm. A few years ago, there was a lot of speculation about a gas cloud falling into it and being consumed by it. At that point, could there be an AGN at the center of our galaxy?
Yeah, so I know what you're talking about. You're talking about the G2 gas cloud. And I think the gas cloud itself was something in the order of one solar mass or something like that. The thing is, the energy output of, or the accretion rate of an AGN is something in the order of one solar mass a year. So in order for it to be an AGN, it did, as far as I remember, it did give a very brief flare, X-ray flare at least, and probably in other wavelengths as well. It could be sort of give a very brief moment of activity, but most AGNs have a somewhat more sustainable, a more sustained fuel source. But I mean, yes, for a very brief time, it did have some AGN activity going on.
Okay.
But
right.
One thing that is interesting is that we, again, with the Milky Way, that if there had been AGN activity in the past, it is a sort of transient phenomena, these AGNs, but we are probably talking on timescales of 1 million years, perhaps a bit more. So it is quite a lot of material it has to be fed.
Okay. So could I ask you to stop sharing your screen?
Mm-hmm.
And then we can see the rest of the participants.
Stop share. There we are.
Okay. And so, as usual, ladies and gentlemen, if you have a question, can you put a digital hand up or wave at me, and I will nominate you. So, questions, anybody? Oh, everybody's gone shy on us, Mikkel. Oh, Tony Morris, can you unmute your...
Unmuted, Paul.
Thank you, Tony. Your question, please.
Mikkel, you said at the beginning of your talk that it wasn't an area that was greatly researched. Is that because of maybe people like Halton Arp and some of his maybe strange theories have dissuaded people from researching?
I'm not sure what Arp has said about it. Perhaps you can fill me in.
Okay, so Halton Arp said a lot of the very bright galactic nuclei didn't lie at the distance indicated by the redshifts.
Mm-hmm.
And he often said that they were co-located with galaxies which we now think are in the foreground.
Mm-hmm.
So he actually lost his research time on the big telescopes because of his theories in this area.
I know. So while I was researching the history of this as well, there was another one whose name I cannot remember. He had a lot of theories about that the reason the cores were so bright was because of gravitational lensing. So I think there was a lot of differing and competing theories at that time. As far as I could also tell is that the resolution and the different telescopes, they were just not, they could just not explore this to a greater degree. As far as I can tell, it was really the radio astronomy that started the interest in these objects again, because optical telescopes, they could not really resolve things much better than what Carl Seifert had done already. And there were no, his article from 1943, it's very, it doesn't come with many controversial statements. It's very just, this is a galaxy, it has broad emission lines. There's not really a lot of things to go on. And I think that definitely also limited the appeal of researching this. As a sort of research for this talk as well on the history, because the history of AGNs is not really my forte. I found a certain Gregory A. Shields, who has been involved in, he did a sort of a brief history of AGN on net. I can share the link possibly on Zoom if that is an option, Paul.
If you can send it via the chat, then everybody can record that. There you go, we've got it.
He goes through quite a bit of the beginnings and the introduction, and I think he was somewhat personally involved as well, at least had some of the pioneers as a supervisor, I think. But he does go into quite a lot of the difficulties in the beginning of this. So, yeah.
Okay, Tony.
You. Yeah.
Tony, did you get the link?
Yes.
Okay, so Roy Gunson.
Yeah, so maybe something that's not answerable, but as the universe gets older, the black holes at the center of galaxies are obviously going to get bigger and heavier. Is it likely that there's going to be more AGNs in the future, or less, as the universe evolves?
That's a very interesting question, because ultimately it comes down to whether an isolated environment is better for AGN activity, or a environment where a galaxy is disturbed quite a lot. If a galaxy is isolated, it needs to, let's say if we have a spiral galaxy, it has its disk, and this disk is actually very stable. And if it's just left to its own demise, then nothing will ever happen. Everything will just rotate very happily around. So in that, what you need to do with this gas that's just rotating happily around is you need to disturb it, you need to take some angular momentum out of it. And the usual explanation people use is an interaction with another galaxy, or even a merger. In that case, then if following that argument, then actually the AGN activity would be less in the future, because there would be less disturbances and galaxy interactions. On the other hand, then you have the galaxies that, if they are left to be just be themselves, then perhaps they have some time to develop a bar system, or a sort of structure that is more beneficial for AGNs, and for an easier way to transport material in. But as far as I can tell, that's not the preferred method. I think the preferred idea is that there needs to be disturbance of the angular momentum of the gas, which usually means interaction with other galaxies.
So in about 4 billion years' time, when Andromeda and the Milky Way collide, there's a chance that one or both of us will become an active galactic nuclei.
Mm-hmm. Yeah, I think so. I think that's a very real risk, because it is quite it is a galaxy-wide event. It's something that can disrupt and input energy in a whole galaxy. So it might be something to be worried about when that time comes, more so than colliding with the other stars.
Okay, thank you for that. Has anybody got another question? Peter Lloyd.
Yes, thank you, Mikkel. Very quickly, to a sort of order of magnitude, how many AGNs are known? Is it a very few, or are they very large? I mean, are we talking about hundreds, thousands, millions?
Right. Yeah, I think so. I'm just doing a real quick run through in my head. We know probably around 100,000 or so of various intensities. Of quasars, I think it's probably more in the order of 1,000 or so. Quasars only account for like 1%. So the very most powerful types of AGNs is only 1% of the whole population.
Oh, thank you. So they're not particularly rare.
No, I guess not. I mean, not to some degree, but the quasars are, I think. Yeah.
Yes, thank you.
Okay, I'm looking for any other questions. Going once, going twice. Ladies and gentlemen, can we give a big Mexborough and Swinton Astronomical Society thank you to Mikkel for an excellent talk. Thank you very much, Mikkel.
Thank you.